And welcome to Sanford Flip Math. This is Sanford Flip Math, the home edition. We're working through AP Calculus right now from the Larsen and Battaglia book. We are about halfway through chapter 4. We're in section 4.5, and today's topic is net change. This is a little bit of a so what for integration. In other words, why are we doing integration? And so I just wanted to remind you of some basic ideas first. And that is the idea of, like in physics, like in algebra, you've been doing this forever, rate times time equals distance. That idea of like, if I have miles per hour times hours, I get miles. And if we were to graph something like that, we would do probably the rate on the y-axis, so like how fast we're going. So this would be like the miles per hour, and time across the x-axis. And as we're looking at rate times time, so this would be like a constant rate. And the idea is that whatever that rate is, we would multiply it times time. So if I was going to talk about for the first 5 minutes, and we're going at 10 miles per minute, that'd be really fast. Maybe we're in an airplane. So we'd go 50 miles, you know, because it's just literally 10 times 5 is 50. So the idea that area is that distance, that rate times time, that's the concept we want to talk about. And so to connect that with what we've been doing, area then, if we're talking about a rate in time, then area becomes the same thing as distance, or technically displacement, because it could be positive or negative. We're going to also call it net change, the change in position. For instance, if I start here and end there, then my net change, my net distance change is what we're talking about. And worth noting that we could be talking about going forward and then coming backwards and then going forward again. And so net change does not have to be the same thing as distance traveled, which so just worth noting, displacement, how far you are from where you when you end from where you start. So position final minus position when we start out initial, that is displacement, which is not always the same as distance, because you might go frontwards and backwards and that kind of stuff. So all of this, area, distance, net change, really is the same idea as what we've been doing is integral. So if the integrand, the inside of the integral, is the rate of change, okay, so that's the rate of change, that's that notation, of whatever f is, then when we do the integral of that and substitute and we subtract, that is the net change of f. Okay, and this net change can be for anything. This could be volume of something filling up, and we have a rate of change of the volume, so we would do an integral to find out how much the volume changed. If it's position and distance and velocity and all that stuff, it could be the rate of change of the position, so therefore integral is going to be position. So whatever the rate of change is about, whatever this rate of change is about, when we do the integral, we found out how much that thing that it's about has changed. Okay, all right, so moving on. All right, let's do some real straightforward examples. Sorry for the scribble, but I couldn't make myself fix the whole page, start over. So, so if I have a velocity of 5 centimeters per second, and if I'm traveling from 2 seconds after I've left to 10 seconds, over that 8 seconds, how far have I moved? What is my final destination compared to where I started? And so if we were going to do a graph of that, just to kind of get a picture of what's going on, again, this looks very similar to what we just did. Okay, so here's 5, because that's constant. That's a constant velocity. And then 2 seconds might be here, and 10 seconds might be here. And I can literally say 10 minus 2 is 8. So that's a change of 8 times the height of 5. So this would be 40 centimeters. Well, I want to take that same concept and do it symbolically. So here I am going from 2 to 10, 5 dt. Okay, so this is notation for that. And so when I do antiderivative, I'm going to say 5t. We're going to evaluate that from 2 to 10. So this becomes 5 times 10 minus 5 times 2. So this is 50 minus 10 is 40, and the units there would be centimeters. Now, in terms of the notation here, this is that velocity, this is that centimeters per second, and then the dt is that idea of a bunch of skinny little rectangles being added up that we're doing 5 times that little bit plus 5 times that little bit. And again, this is summing them up. This is adding them up. So that dt was in seconds, and centimeters per second times seconds. When I add up all those centimeter rectangles, I get a bunch of centimeters. Okay. All right, let's do the same thing again. Only this time it's going to be a little, just a touch more interesting. Okay, so again, I want to do the graph just to kind of tie it all together. Okay, and it's looking something like this. And we're talking about the first 5 seconds. Well, if it's the first 5 seconds, that's from when it starts at 0 to 5 seconds. Okay, so the first 5 seconds technically means from 0 to 5. Okay, so we're going to do the integral from 0 to 5 of 4 minus x dx. And I did not leave myself enough room there, so we'll have to drop down here, and then we'll pick that up in a second. Now, I'm just going to go ahead and do the integral. Okay, so the antiderivative of 4 is 4x. The antiderivative of x is x squared over 2. We're going to evaluate that from 0 to 5. Okay, so now we're going to substitute. So 4 times 5 minus 5 squared over 2 minus, well, that's going to be 0 and 0, so I'm just going to go ahead and do that. So this is 20 minus 25 over 2, also known as 40 over 2 minus 25 over 2, 15 over 2, or for those of you watching at home, 7.5 or 7 1/2. I don't care which way you like it, or whichever way you have it, it doesn't matter. Worth noting again that this rate was centimeters per second and 5 seconds. So the distance will be in centimeters, and whichever way you like that. Now, I would like to back up for a hot second and talk about what's going on. Back up. That's kind of funny. That was a pun. I didn't even know that. If I thought about this area, this would be 1/2 times 4 times 4. So that's 8. This little guy right here would be 1/2 times 1 times 1. So that's really 1/2. There's a but. Yeah, it's underneath, so it's negative. So this was 8 minus 1/2. So the idea was, if we wanted to illustrate this, this person, this thing, this item, whatever, went forward 8 centimeters and then backed up 1/2 centimeter. Okay, so now the question is, what's the distance traveled? What's the actual distance? Well, it's really not 8 for displacement is 7.5. That means we started out, we finished 7.5 centimeters from where we started. The distance traveled, though, was we traveled 8 centimeters and then backed up 1/2 centimeter. So that distance is really 8 plus 1/2, or 8 1/2 centimeters. Now, if you were going to do that with integrals, you would do separate integrals. So we would actually do the integral, and we'd have to know where this sign change happened. We would do the integral from 0 to 4 of 4 minus x dx plus the integral from 4 to 5 of 4 minus x dx. But there's a little bit of knowledge that you have to have here. Since that's underneath, we'd have to make this positive, so we would just do absolute value of it. So we would do this integral and we would get 8. We would do this integral and we would get negative 1/2, and they'd say, oh yeah, make it positive. Okay, so there's your 8.5. Okay, so conceptually not that deep, but there are going to be some things that you kind of have to watch for. Okay, so just a heads up, you're going to have to watch wording, you're going to have to watch for the details. Okay, all right, I got 2 more examples I want to do, and I'm going to keep it moving because I really don't I don't want to keep you here forever. So you know how to pause, you know how to back up if it's going too fast. Okay, displacement is just net change, and net change I can do by just literally doing the integral. I don't have to think, I just do it. Okay, so this is velocity this time. and we're talking about from t equals 1 to 5 seconds. So this is my setup, and you need to know that you need to be able to do this setup. This is not a big deal. Just write it out. Ta-da. All right, we can do antiderivatives term by term. So that's what we're going to do. So this is t to the 4th over 4 minus 10t cubed over 3 plus 29 over 2. And then we need to evaluate it from 1 to 5. Okay, so this is me being careful with my notation. All right, so t to the 4th at 5, that's 5 to the 4th. That is 625 over 4 minus, well, this is going to be t to the 3rd. That's 125 times 10 is 1250. So I'm just substituting stuff in. Plus, that's 25 times 29. Okay, now that one I can't do in my head. So 25 times 29, I'm breaking out the calculator, is 145 over 2 minus 20 times 5 is 100. 100 minus, okay, we're going to do the same thing, only we're going to put in 1. Well, this will go much faster. All right, so this is 1/4 minus 10/3, 29 halves minus 20. All right, and then we got to do some mathy stuff. So I'm gonna type this all in, but I'm gonna pause while I'm doing it so that you don't have to listen to me type. All right, so apparently I had a typo right about here, and that was supposed to be 725. So let me pick up where I left off there. Okay, so I caught it because my answer wasn't coming out right. And then I had a typo here too. Rough day, sorry. Long Sunday afternoon. All right, so type all that in, I get this. Type all that in, I get this. Do the subtraction, I get this. So this is 32 over 3, or if you prefer the 10 point, lots of 6s, feet. Remember, this was displacement. So now the problem is this. The second part of the question wants to know the same idea, only they want to know distance traveled. Well, distance traveled, again, from 1 to 5. It's the same idea, but there was some negative stuff. I mean, you can see the negative stuff that showed up. Well, technically, that may or may not come from that. But the issue is what's going on with the graph. So let's take a little look-see. Okay, so I'm going to type x cubed minus 10x squared. The graphing calculator is set up where it's supposed to be all about x. So we have to kind of just make this work. All right, so x cubed minus 10x squared plus 29x minus 20. Okay, and I'm interested in from 1 to 5. So I'm going to for sure I'll go from like -1 to 6, and we'll just kind of go by ones. And I don't know what's going on here. So I really don't. So I'm just going to say -5 to 10, and we'll just adjust it as we need to. I'm just guessing here. Oh, that was a pretty darn good guess. I'm quite excited. All right, so remember we're going from 1 to 5. So from here, this is 1, 2, 3, 4, 5. So I'm going from 1 to 5. So let me do a little bit of a sketch here. Here's 1, 2, 3, 4, 5. Okay, it looks like it crosses at x equals 4. Let me do a quick look at the table. X equals 4 is 0. X equals 5 is 0. Okay, so that's good. And I know it crossed, well, I believe it crosses at 1 also. Yep, those are all of the zeros for this guy. And I don't know, it goes up somewhere else. It doesn't matter how far it goes up. Now, what we are interested in doing, remember, is we're interested in finding the distance traveled, which is really area. And the thing to note here is this little piece is negative. So what this means is we're going to have to do the integral from 1 to 4 of, I'm going to say f of t, plus the integral from 4 to 5. And then the catch is we know we expect this to be negative, so we're just going to make it positive. Now, in terms of the steps, I'm not going to bore you with all the details. It would be the same stuff. We'd be doing antiderivative, and we'd be putting 1 and 4 in. So instead of putting this 5 in, we put in 4, do the subtraction, and that would be this part. That would be this part. And we do it again with 4 and 5. So here's the 5 put in, and then we would have to put 4 in here and go from there. Okay, so hang on just one sec. Okay, so I went ahead and found these separately, and as noted, this is positive. We're going to make this positive. So this becomes 1125 plus, and then, all right, so let me do some typage here. So 11.25 plus, yep. So that becomes, so this is plus 0.5833, which is 11.8, lots of threes, also known as 11 5/6, which is 71/6 if you wish. And again, this will be in feet, okay, in whatever form you like. All right, I'd like to show you one other sneakiness, because sometimes you get to use the calculator on this, and I want to point something out to you. And I really want to do another example, but I think I'm going to be out of time, so I will not. I'm going to turn this equation off, and you wouldn't have to type it in this way. I'm just going to type it in this way for lack of time. And I'm going to do alpha trace. And so really what I'm doing is the absolute value of that thing. Okay, so look at this graph now. Okay, is that going to show up? Please let it show up. Funkiness. How can I get that to show up better? Getting some glare here. Let me turn that down. Maybe that'll help. Is that going to work? Wow, that's really not good. I'm trying to get this to show up, but it's not helping. Not working, huh? Well, this is not cooperating, but maybe we can catch a little bit there. The thing to note here is everything that was negative, because we did absolute value, is now folded up to the top. Okay, so I'm just going to kind of add on to this graph this that I have sketched here. So this guy comes up, this is still up, this comes up, and then this is still up. Now we really only care about from here to here, right, between these two. But the thing to note here is this is now positive. What that means is, now we don't have a cute way to do this symbolically, analytically, but I can do the antiderivative, or I can do the integral from 1 to 5 of the absolute value of that whole function. Now I can do that in the calculator. I can type that in. So this is the t to the third minus blah, blah, blah. And I can just type this in, but note that the absolute value bars need to be inside the function, inside the antiderivative, inside the integral. Okay, so this becomes, this would just get us to the 11 5/6 or the 11.83 in one shot. Okay, so if you have access to a calculator, you don't have to break it up. You can just make everything positive for the function and then do the integral right out of the chute with Math 9, which is the function integral, or second calculate 7. I just want to point one other thing out, and then I will cut you loose. And that is that there is a word, a vocab term in the section called marginal profit. And I just want to note that marginal profit is the rate of change of profit. We're not going to do an example of it right now, but it might come up in the homework. Marginal profit is the rate of change of the profit, how fast the profit is changing. So if you wanted to know the change in profit, the net change in profit, then you would have to do the integral of the marginal profit. Okay, so that was just a quick heads up on that one. Just so if you didn't, I've never, I don't see that term very often because I'm not an econ guy. All right, well, I feel like that was a lot to try and get in, even though it's a very simple topic. Net change is basically the integral of the rate of change, and that's it. So thanks for coming. This is Sanford Flip Math. Bye.